Okay, so here is this is our driving frequency. This is the amplitude of the oscillator here. Now remember these curves, if there's no damping, these curves, there's an asymptote here, right? There's like some resonant frequency here. This thing just goes up forever, right? But because there's damping, it kind of stops at some point and comes back down. Okay, now what they're saying is let's increase the damping of the system. Okay, well, as you know, that there's going to be something that's going to happen to this curve, right? So if you increase the damping, that's the thing that takes away energy from this, right? There's something's going to happen to the broadness of that peak. Broadness. Okay, I'm going to go with broadness. The broadity, the broaditude. Okay, how wide the peak? The width. That's the word I'm looking for. Something's going to happen to the width of the peak, so talk about that. Something's going to happen to the height of the peak, right? And something's it's going to shift horizontally. It's going to shift either right or left if you increase the damping, okay? And then also something else happens at the extremes, okay? You know how to do this. You can draw this peak, okay? All right. So now we've got this mass, and we've got a sine wave vibrator attached to it, okay? And this is the mass oscillating up and down, right? Now remember, it's driving. It's the same frequency as the natural frequency. So the the driving frequency is equal to the resonant frequency, okay? Remember that has certain implications, right? So like the amplitude is high, and then it's 90 degrees. The mass is 90 degrees behind the driver, which is another way of saying that the driver is 90 degrees ahead. Okay, so 8 seconds, what you're going to do is you're going to find where 8 seconds is on this thing, right? And then understand that the driver is 90 degrees ahead of it, right? Remember on like a sine wave, right? 90 degrees is, this is 360 degrees, right? So 90 degrees is from here to here, from there to there, from there to there, right? 1, 2, 3, 4. There's 490 degrees, is it, right? So understand what 90 degrees is. Understand that the driver's 90 degrees ahead of wherever the mass is, right? So find where the mass is, decide where the driver is. You can even say which way the driver's going if they don't ask for it. They should have. All right, anyway. Okay, the vibrator is switched off. The spring continues to oscillate. The Q factor is 25. So what we're going to do here is we're going to say Q is 2 pi. This is the resonant frequency, right? And then energy stored over power lost. All they want us to do is just solve for this factor right there. We don't need to solve for this or this, just simply whatever that is in the parentheses, okay? So put 25 in for Q. The frequency is, well, figure out what the frequency is. Looks like it's 8 seconds is the period, right? So T is 8 seconds, okay? So the frequency is going to be 1 over 8. So plug that in. That's our resonant frequency. Whoop. The formula I'm using there is what? Frequency is 1 over period, okay? So plug 25 in there, 1 over 8 in there. Solve for whatever's in those parentheses, okay? Understand that this has units. The units will be joules divided by the power lost is going to be joules per second. Okay, so this actually has the units of seconds, which is interesting, right? Since this has the units of 1 over seconds or hertz, the units just cancel out, right? Q is a unitless thing.